Okay, welcome back. In this lesson, we have laid the groundwork already to finally finish our complete description of Maxwell's equations via differential forms. We understand all the differential forms, and we understand all the relevant operations, and we understand how those operations tie to the curl and the divergence, which the familiar form of Maxwell's equations in the standard vector analysis system have come down to us. So now we're ready to actually finish this up. This might be a little bit of a long lecture tying it all together, because I just want this to be the last lecture on this subject. So let's begin and see if we can get through the entirety of the material. So where we left it is we had come to the understanding of how to calculate the divergence of a vector using a method of differential forms. First of all, we end up treating the vector as a one form, so we have to convert your standard vector to a one form. And then we understood that if you have a one form in three-dimensional space, when you take the Hodge dual of that one form, you end up with a two form, and you take the exterior derivative of that two form, and you get a three form, which is one-dimensional. And then you take the Hodge dual of that three form, and you get a zero form, which is also one-dimensional. And so this divergence of a vector translates to the Hodge dual of the exterior derivative of the Hodge dual of the equivalent one form. And so we can replace the left-hand side of this Maxwell's equation with that term. The right side has a source on it, so we're just going to leave that alone for now. Likewise, we came to understand that the curl of a vector can be converted into the language of forms by turning the vector again into a one form. The electric field is a one form. And by taking the exterior derivative of that one form and then the Hodge dual of that one form, we get the equivalent of the curl. It works out mathematically to have the same information. And if we operate in an environment where everything is static, and I'm not going to struggle with the difference between static and stationary here. I'm just going to just say magnetic field is not a function of time, so this term is zero. Then we have this Maxwell's equation. That is conditional on this term being zero, however. Then what we learned is that, all right, so we're good with the electric field being transformed into a one form, and we understand that because the electric field has been classically called a vector field, in particular a polar vector field. But we understand that the magnetic field is an axial vector field, a pseudo-vector field. So we had to repeat the analysis for the pseudo-vector field, and we understood that that has to be modeled by a two form. So where I see E, I see a one form, but where I see B in green here, I see a two form. And we now realized, when we marched through this, and we realized that the curl of a two form has the same structure as the divergence of a one form. In other words, the curl of a two form is the Hodge dual of the exterior derivative of the Hodge dual of a two form. And again, in a context where there's no sources and where there is no time dependence on the electric field, we can write this Maxwell's equation in this very tight little form using differential forms, tight little structure. And then the famous divergence of the magnetic field equaling zero, we understand that the magnetic field converted to a two form, the divergence of a two form is the same structure as the curl of a one form. And so we get this famous equation. I will say that these last two in particular, we can take the Hodge dual of both sides, and we end up with something a little more plain. The exterior derivative of the magnetic field two form is zero, and the exterior derivative of the electric field one form is zero, because we take the Hodge dual of both sides, and so it's a little simpler. Not that it matters much, but it saves a step if you were to calculate it that way. So now the problem we're going to deal with is there's all these caveats, right? There's this caveat of no sources, although I left it in here, but the big caveat is that the time dependence was ignored. So what we really need to understand is that that when we are doing this work, E, which is a one form, is a function of x0, x1, x2, and x3, where our x0 is our time. Right? I call it time because in the standard notation, I don't want to call it notation because it's more than notation, right? The standard mathematical architecture used for electromagnetism usually has time labeled as t, whereas the standard architecture used for differential forms, we use this x0, 1, 2, and 3, where x0 is the time variable. And likewise, the same is true of the magnetic field, right? Sometimes we can just write it as b of x mu, something like that. That's another way of, it's a shorthand. This is shorthand for each other. Sometimes it would just be b of x. But you do have to remember that we're now talking about 4 variables, and that's what we're going to have to do to make all this work. We're going to have to go from 3-dimensional space, which is so standard, and we have been using 3-dimensional space up to this point, but we now have to go to 4-dimensional space because we have to add this time variable. So we now have 4 dimensions. And furthermore, our metric is no longer going to be Euclidean. We're now going to have to use a Lorentzian metric. And not a big problem, but we have to make sure we keep track of all that. So that's what we're going to do now. We're going to sort of tie everything together into a 4-dimensional structure so we can include time, and then we're going to determine how to create Maxwell's equations that way. All right, so let's begin. So our first process will be to deal with these 2 equations. These are the source-free equations, right? That's what they're called. We're going to call them the source-free equations as opposed to the sourceful equations, right? That is, this one is a sourceful, this one is a sourceful. The current and the charge density are the sources. So the source-free equations are the ones that automatically have nothing on the right-hand side. So we are going to work with those equations first. So our first step is exactly the same step we took previously. We are going to begin by modeling the magnetic field as a 2 form. So when we see B, when we see the symbol B here, I'm not going to put 2 lines under it like I did in the previous lesson just to emphasize that it was a 2 form, or 1 line to emphasize it was a 1 form. Now we just know, right? We just know that the magnetic field is a 2 form, and here is the 2 form structure. It's the same 2 form structure as 2 dimensions, right? That's important because remember, the magnetic field we still understand as a vector in the world, so it has to be an object that has 3 dimensions to it. Now we do have access to a dx0, but we're still modeling the magnetic field exactly the same way. Likewise, the electric field. The electric field we're going to model as 1 form, just like we did before. So this step is actually the same, even though we now have access to a dx0 term, right? Even though we have access to this term, we're not adding it into the model of B and E because they are still 3-dimensional objects. But what we will do is we'll take these 3-dimensional objects, or we'll take these 2 objects we've created, and we're going to bind them together. We're actually going to mix them into a single object that we're going to call F. And F is going to be the electromagnetic field. Now we can call it the electromagnetic field 2 form if we like, because it is going to be a 2 form. You can see that on the left-hand side is F, and it's defined through B, which is a 2 form. So if you're going to add something to a 2 form, it better be a 2 form. Well, this is a 1 form wedged with dx0. So this 1 form wedged with dx0, you can kind of see what it's going to be. It's going to be E1, dx1 wedge dx0, E2, d2 wedge dx0, and E3, and just to drive the point home, I'll actually draw it out, dx0. So each one of these is going to have a dx0 added to it. right? Just like that. So now both this term and this term are two forms, and you can add two forms together. But notice now we're using all four of the different dimensions, right? The time dimension gets attached right here to the electric field. So they're now, the electromagnetic field really is a bunch of two forms, but our electric field has somehow been kind of augmented in time. And that's an interesting thing. It's the magnetic field is living entirely in space, but the electric field part of the electromagnetic field has this time element attached to it. And that, that is what makes this so interesting. So with that in mind, we will start operating on this object. This integrated object contains the electric and magnetic pieces of the electromagnetic field all bound together in one mathematical object. And our ability to turn Maxwell's equations into a differential forms structure is going to be completely operating on this object F. And I'm just going to demonstrate how that works. All right, so I'll do a bit of foreshadowing regarding number 3. And ultimately, those two Maxwell's equations are going to be the exterior derivative of this electromagnetic field two form. The exterior derivative of that equaling 0 is going to be the equivalent of these two of the four Maxwell equations. So that's sort of the end here. So the way we're going to do this is just through straight up demonstration, right? We're just going to demonstrate that that's the fact. So our first step will be to calculate, in this demonstration, we're going to calculate the exterior derivative of the electromagnetic field. And this is now our new electromagnetic field. It's this bound together thing of the electric and this makes no sense. See, this makes no sense, right? I can see right away because I know B is a 2 form and the exterior derivative of 2 form is a 3 form. So that's a 3 form. I know E is a 1 form, and a 1 form wedged with a 1 form is a 2 form. So this is a 2 form being added to a 3 form. Now, there are algebras where you can do that, right? There is an algebra that's over-encompassing where you can add what is equivalent to a 2 form to a 3 form. That's what geometric algebra actually allows you to do. And it's a very interesting point. It's called a multivector, but that's not what we're dealing with here. We're not dealing with multivectors here. This is simple, more elementary 2-form math. You know, we'll talk about maybe multivectors if we do a section on geometric algebra. So I know right away I made a mistake there, and that mistake was D. What I'm trying to show is that the exterior derivative of F will distribute, right? So I replace F with its definition, and then I show that I can take the exterior derivative of the first piece and then the exterior derivative of the second piece. Now we're fine, right? Because this is a 3 form and this is a 3 form. Okay, so then this is what we want to calculate. Now, as part of this calculation, what a lot of books do is they separate the exterior derivative into a spatial part and a time part. And I'm not too big a fan of that because you can just calculate this. You can just use the rule of exterior derivatives and calculate this straight out. And that rule, remember, was if your form alpha is this sum over this multi-index where dxi is representing in the 2-form space, it's all of these guys here, right? These are the basis vectors of your space of 2 forms. And some coefficient alpha. And remember, alpha is a function of space-time now, right? It's a function of time and x, y, and z. So the exterior derivative of alpha is the sum over these indices, but then there's this internal sum also, right? And this internal sum goes over the index 0, 1, 2, and 3. The 0 part, that's the time part. Right, and so so you're always wedging whatever piece of the sum you're doing. You're wedging that into this multi-index. So this exterior sum is a sum over these multi-indices, and this interior sum is a sum over the space-time indices. So this allows you to break this down, right? if I blow up this interior sum, right, this contraction, if I blow that up, I get these four terms, right? There's this time term, right, where we have the time derivative of the coefficient, and then we wedge the time one form with the multi-index. So I'm still summing over the multi-indices, but now I've broken up that inner sum. So this part here is sort of the space part of the exterior derivative, and this part here is the time part of the exterior derivative. But it's still the same. This is still literally the definition of the exterior derivative. So I could break this up into the time-like piece and the space-like piece. I don't know if I like the word, that's sort of my language. This adding the like to it is probably wrong because that implies there's some kind of causality issues here, but that there aren't. I'm just literally breaking the sum into the time chunk and the space chunk. And then I can say the exterior derivative of any form is simply the time chunk exterior derivative plus the space chunk exterior derivative. You have to have them both to get the full exterior derivative. So the thing that's important to see here is that the time chunk exterior derivative will always wedge a dx0 into the multi-index, and the space chunk will always wedge some space piece into the multi-index. And that simplifies a little bit of our thinking, but not too much really, right? Because now if I take the exterior derivative, I break it into its space piece and its time piece. So likewise, once I use this, once I distribute this exterior derivative over the parts of the electromagnetic field tensor, I find myself taking the space exterior derivative of E wedge dx0 and the time exterior derivative of E wedge dx0, and then the space derivative of the space exterior derivative of B and the time exterior derivative of B. And, you know, I can get a little simplification here because I know that the space exterior derivative of something is always wedged with dx0, but this already has a dx0 in it, so I know that's going to be 0. I know this is going to go away. But that's all I really know because the space part will not necessarily go away, right? There is one space piece in E, right? Because remember, E is defined, you know, straight up as a one form, so it has space pieces only. But the space exterior derivative has all three of the spatial one forms in it. So some will survive and some won't, right? So that doesn't, so I mean, it simplifies the calculation because I don't waste my time with the space part, right? And for B, it's the same thing. The space part, some will survive and some won't. And the time part, they'll all survive actually because B has no time piece in its definition, right? The magnetic field 2 form, it's all purely spatial. So when I take the exterior derivative time part, I wedge with dx0 in front everywhere, so they'll all survive. So it's not a huge simplification. There is a more elegant way to proceed onward from here, but I decided, you know what I'm going to do? I'm just going to calculate it. I'm just going to go ahead and straight up calculate it. So I'm calculating all of these three things. And I'm just using this basic formula, these basic formulas right here to do the calculation. And ultimately, the calculation is this guy, right? And ultimately, this guy is just this guy here, right, which we learned about in earlier lessons. So you can think of it this way. Just take the darn exterior derivative of df and drag everything to 0 that deserves to be 0. Anyway, so let's do this calculation, right? Let's take this spatial exterior derivative of the electric field wedged with dx0, right? So here's the electric field wedged with dx0. We're going to take the spatial exterior derivative. And we end up with this line down here, right? It's the partial derivative with respect to x1 of E1, dx1 wedged, dx1, dx0. So right away we know that's the one that dies because we have dx1 wedged, dx1. Then we have the second partial derivative with respect to x2 of dx1 of E1, dx2, dx1 wedge dx0. So this survives because you have 2, 1, and 0, no duplicates. And then you have the partial derivative with respect to x3 of dx of e1, dx3, dx1, dx0. So that survives too. So this one's going to die, but those two are going to live. And that takes care of this first term. And then the second term and the third term are similar, right? It's kind of tedious, but here's the second term, where we're now taking the only difference really is we're changing e2, and this becomes dx20 wedge dx0, dx20 dx0, dx20 dx0, wedge with dx3, wedge with dx2, wedge with dx1. Obviously, this is the one that's going to die, dx2 wedge dx2. And the last one, the only difference is we're now doing partial derivatives of the third component of the electric field. And its basis vector is dx3 wedge dx0. And then we're throwing in dx1, dx2, dx3, and obviously this third one that dies because of dx3 wedge dx3. So I guess it's not even particularly lengthy if you can cut and paste. So this one we've calculated. So now we can calculate the spatial derivative part of the magnetic field, 2 form. And oops, I don't see why this should not be a plus. This should not be a minus, that's a plus. So we're going to calculate this. So the spatial derivative part, very similar, except, so now we'll start with b23. We'll start with this first term, and that's the spatial derivative of b23 with respect to x1, dx1, dx2, dx3. Spatial derivative of b23 with respect to x2, dx2, dx2, dx3. So that'll go away. And the spatial derivative of b23 with respect to x3, dx3, dx2, dx3. So that one goes away. So for the magnetic field, we lose 2 of the 3, which makes perfect sense, right? We're taking the spatial exterior derivative of something that's already fully spatial. So there's only one more spatial variable we can add in there for this term, and that's dx1. So only the dx1 term will survive. So those two will go away. And then when we do the calculation for this bx31, the same thing's going to happen, except in this case, we have 131, that'll go away, 231, that'll survive, and 331, that'll go away. And then this last term, b12, dx1, dx2, you can predict right away. The only one that'll survive is the third partial derivative, or the partial derivative of b12 with respect to x3, dx3, wedge dx1, dx2. And that's going to be this last term here, dx3, dx1, dx2. This one will die because it's got dx2 wedging with dx2, and this one has dx1 wedging with dx1. So a lot of terms are going to go away. And then, lastly, we take the time piece of the magnetic field, and what we discover is this time there's only one derivative to take, and that's the partial. This is the only one that has a time piece left in it, and right, because the time part for this term went away, and so there's only one derivative to take, and that's the derivative of the coefficients with respect to dx0. So we have the partial derivative with dx0 of 2, 3, dx0, wedge 2, wedge 3. And it's pretty clear that all 3 terms are going to survive. So that term will survive because you're adding a dx0, and none of these have a dx0 in it, right? So all 3 of these terms survive. So now we can just get rid of the ones that don't survive, right? And here I actually just crossed them out. I've cut and paste that over there, and I crossed them out to show you which ones don't survive. And then we just keep the ones that do, right? We just keep the ones that do. So the first set, so I've reorganized them. So some of the ones that do, let's look at the time derivatives of B that survive. Remember, all 3 of those survive? Well, if we look at it, we can shuffle this dx0 to the back in each case. Right now it's in the front. We can shuffle it to the back. And when we do that shuffle, right, we move it 1, 2. So you get a sign. Remember, this is totally antisymmetric, so you get a sign change and a sign change. So the two sign changes cancel out, so you have no sign change in the end. And so you get, for this first piece, b23 dx2 dx0, and the partial derivative with respect to x0, and then dx3 dx1, dx1 dx2, and they're all wedged with dx0. So this part here looks like that part, this part in red. And the part inside, well, that's just the magnetic field 2 form, right? That's what that is. So we simplify this, and we just write the time derivative of the magnetic field 2 form wedged with dx0, right? Wedged with dx0, that's what this piece of what's left over from all the work we did. Remember, in the end, this is all supposed to be the exterior derivative of f, right? That's what all of this is. So this one part of the exterior derivative of f, this piece here, we've recalculated down here to be just this thing in green. Likewise, we take the magnetic field parts that survived from the spatial exterior derivative, and we combine those together. And when only 3 of them survive, remember, look how many, 1, 2, 2 from each component die. Each component gives you 3 different parts, and 2 of each of those 3 die. So you're left with 3 pieces, and that's these 3 pieces here. And that's all comes from this center line. And those 3 pieces can be combined to give us a partial derivative with respect to x1 of b23, partial derivative with respect to x2 of b31, partial derivative with respect to x3 of b12, times the basis 3 form. This basis 3 form is the purely spatial 3 form. Now remember, we're dealing with 4 dimensions. So 3 forms aren't one-dimensional anymore, right? 3 forms are 4-dimensional. And 4 forms are one-dimensional. So this is just a purely spatial 3 form. But notice over here, you don't have a purely spatial 3 form, right? You've got 3 forms that have space parts and a time part tacked on at the end. So these guys are in a sense orthogonal to, these guys are not, these guys have a time piece and these guys do not. And then we take what's left over from the electric field. And when we take what's left over from the electric field, we're combining these guys together, and by reshuffling the order of these various 3 forms, we end up with, again, mixed time and space 3 forms, but we can pull out the time 3 form and or the time 1 form and leave behind this 2 form, and the coefficients of these 2 forms end up being the curl of the electric field. And you can kind of see where this is going, right? Here's something that looks like a curl, right? This looks like a curl. This looks like the time derivative of a magnetic field 2 form, and this looks like a divergence, right? And so ultimately that's correct. That's the way this is going to work, right? Because this and this both share dx0, but this does not have any dx0 in it at all, right? Now, we know from Maxwell's equations, we know that the divergence of the magnetic field is 0. And that's exactly what this is, right? These are the components of the magnetic field vector, right, inside this little thing here. And therefore, we know that this has to be equal to 0. And also from Maxwell's equations, we know that the curl of the electric field and the time derivative of the magnetic field combined, that equals 0 as well. So our next step is to sort of translate this into vector language. Well, to do that, we just kind of combine everything we can combine. We can combine this. Well, first of all, we recognize that this is the exterior derivative of the electric field right? The electric field is a one form, the exterior derivative is a two form, and that's exactly what this is. And we know that this is what's left over when you take the exterior derivative of a one form. You get a two form, and that's what this is in here. Now, what we would do normally next is, if we were really interested in this being a curl, is we would take its Hodge dual to convert these two-form basis vectors into the one-form basis vector, so you have what looks like a curl. But right now, we just leave it this way. And this, of course, is just the time derivative of a two-form. So this is a two-form, this is a two-form. You add it together. You can wedge it with dx0 to get a three-form if you want. And, well, that's required, right? So this is a three-form. And then this piece is a three-form, but the coefficient is straight up the divergence of the magnetic field two-form, which we know how to write down. So we can definitely take this piece and we can write it down as the Hodge dual of the exterior derivative of the two-form. So the exterior derivative of the two-form is a three-form. The Hodge dual of the three-form is a zero form, which is what this is, a scalar. And then you have, of course, the three-form basis vector over here. Now, when we look at this, now we have to apply our physics. We know that this guy has to be zero, right? We know it has to be zero because we know Maxwell's equations. We understand physics. There's nothing about this that forces dB to be zero, right? We're just showing that the exterior derivative of the electromagnetic field tells us something, or contains this information, or contains this structure, right? And sure enough, it contains something that looks like the divergence of B, but we know from our vast knowledge of physics that this guy is zero. Now, we also know that del cross E, we also know this Maxwell's equations is true. And we understand that in the concept of differential forms, del cross E is, we know that it is the Hodge dual of the exterior derivative of the electric field one form, right? The electric field one form, the exterior derivative is a two form, and the Hodge dual of a two form is back to a one form. And this guy here is a vector. So this is the one form associated with the vector that is the curl of the electric field. So this isn't quite a match, though, because we only have this without the Hodge dual. But imagine if we took the Hodge dual of this whole thing, right? We would end up with the Hodge dual of dE plus the partial derivative of the Hodge dual of B. I don't need to. There, right? That, well, the Hodge, remember now, B is, we've chosen to make it a two form, so the Hodge dual of B is going to be the B one form, right? This is sort of a two form. The Hodge dual will be a one form, which is associated with a vector. So what I have in here is sort of the Hodge dual of Maxwell's equations, which would be d by dt of the Hodge dual of B, right, equals zero. So I know this guy's zero, and the Hodge dual of both sides will also be zero. So I know that this is zero, right? And therefore, I can say that, hey, Maxwell's equations, those two, are embodied in the idea that the exterior derivative of f is equal to zero, right? So that's kind of cool, right? And but that takes care of just two of the four Maxwell's equations. So you could ask the question right now as well, okay, how profound is this? Is this just some bookkeeping exercise, right? We always have that question. Is this just a bookkeeping exercise? And it really comes down to how capable are we of, this is my opinion now, how capable are we of interpreting the electromagnetic field to form? Is that interpretation something that gives us insight where now we can say, what do we mean by the exterior derivative of a two form equaling zero? And if that's the case, does that help us understand something about the nature of electric and magnetic fields when combined together in a two form? And specifically in the two form of the electromagnetic field. And I think the answer there is generally yes. We're not going to go into that in this lecture. But no, this is more than just bookkeeping. The fact that this can be done and that you can end up with this nice simple equation for these two Maxwell's equations, right? The fact that we're taking, these two kind of basically messy, complicated, and kind of difficult to understand, right? Why would this be? And break it down into something combine them together into something so nice, I think there is some profundity there. There obviously is some profundity there. The question is how actually useful is it be? When you're faced with a problem in electromagnetism, certainly as an engineer, you're going to go right to this. Right? You're not going to go start from here. So anyway, so now the question is, what about the other two? So let me check how long this video is and decide if we want to do that in a separate video or just push on.
Okay, I think I can move relatively quickly through these second two Maxwell's equations. Actually, I think there's time for this. And it's very similar, right? If this was a 0 and this was a 0, it would be the exact process that we did over here, right? It would just be flipping E and B. So the whole problem comes down to sort of understanding what to do with the charge density and the current density. So we begin the same way. We're going to model the magnetic field as a two form, which is the correct modeling because, as we've said earlier, it captures the parity inversion behavior. And we're going to model the electric field as a one form, which also captures its parity inverting nature. And we are going to combine them into the same electromagnetic field, F, right? We're going to go E wedge D0 to turn the electric field one form into a two form, and we're going to add it to the two form of the magnetic field. And you'll notice that this addition I'll just remind you that this addition will be basically disjoint in the sense that the two form components of the B field are these spatial ones, and the two form components of E field wedge dx0 will all be a space and time two form, right? A two form that wedges a space one form and the time one form dx0. So all the electric field components will live in these time wedged two forms, and the space components will be in the magnetic field wedged two forms. Okay, but that's the same one we did before. But now the difference is we're going to create the forecurrent. Right? So the forecurrent is going to be the current vector, right? The current in the x direction, y direction, z direction, with the x, y, and z basis vectors, where I'm now using sort of the manifold notation of the tangent space basis vectors in the coordinate basis, right? Which is, direct substitution for ex, ey, and ez, or I, k, j, depending on how, or I, j, k, depending on what field you're arriving here from. But we take those three and we give them the spatial components, but we give the charge to the time component. So this is now the four vector that will represent the current. But notice that the charge is considered to be the current that's in the direction purely with time, right? It doesn't have any spatial direction. It's the directions associated entirely with time, which I find fascinating. I don't know why. I think that's really an interesting way of blending these things together. This is not a big mystery, nor is it unique to this particular branch of study. Having a forecurrent is totally normal in relativity theory. But now I'm going to take rho, and instead of calling it the charge density, I'm going to make it the zeroth component of the four vector for the current four vector. So now we have it where everything has an up and down index all the way for every component. So rho now becomes j superscript 0. And now we convert this vector to the four current one form, right? And we do this by doing the one-to-one correspondence between the vectors and the covectors, and we take these up indices to down indices. But now we do have to remember, now we're dealing with a 4-vector, and we're dealing with the Lorentzian metric. So this is fine. You can just simply lower the indices. That's completely fine. But we do have to remember that the superscript index no longer equals the subscript index for the 0 component in the convention we're using. It actually equals the negative of that. That's a very standard relativistic thing that we've covered in previous lessons. But understand now it's no longer the straight up Euclidean metric anymore. It's Euclidean for the space parts, but this time part introduces this negative sign. So now this J1 form, if you really were to compare it to the 4 current as we originally wrote it, will have minus rho here, right? Minus rho here. We could have also written, it wouldn't have been very reasonable to write minus J superscript 0 dx superscript 0, right? That's not totally very conventional to have these two superscripts together, but remember, J superscript 0 is a number, so minus J superscript 0 is a number. It equals J subscript 0, so you could do that. I just don't want, that would just, the beauty of the notation is that minus sign is tracked for us just by lowering the subscript and knowing that these things are not necessarily equal. However, remember, these three are equal. Anyway, the upshot of all this is that you end up with the 4 current 1 form. And now we can start tying these things back together again. So now this time, we are going to show that this expression, the Hodge dual of the exterior derivative of the Hodge dual of the electromagnetic field 2 form, equals the current 1 form that we just assembled. And we're going to show that this is equivalent to those 2 Maxwell's equations. And I'm just going to demonstrate that this is the case. First, we do some logic testing. This is a 2 form in 4-dimensional space, right? So we have a 4-dimensional space, and F is a 2 form. So the Hodge dual of a 2 form in 4-dimensional space is another 2 form. So this object right here is a 2 form. Even though F is a 2 form, it doesn't change because the 2 forms are Hodge dual to themselves. And then, just to be clear about that, remember that if the vector space, the underlying vector space V is a 4-dimensional, then the covector space is 4-dimensional. The 0 forms are still the functions, and the 4 forms are 1-dimensional space with this single quadruple wedge product. Then the 1 forms are Hodge dual to the 3 forms, and the 2 forms are Hodge dual to themselves, right? In 3-dimensional space, it was different, right? In 3-dimensional space, I could have sworn I did one of these for 3-dimensional space. But basically, for 3-dimensional space, it's pretty easy. You would lose this, right? And there would only be one 3 form, right? It would just be this single 3 form, and then you would lose this, and then you would lose all the 2 forms with a 0 on it, right? So you'd end up with these 3 2 forms, these 3 1 forms, this 0 form, this, the 4 form goes away, right? And you're just left with the 3 form. And so now 1 forms are dual with 2 forms, right? That's the way it was for 3-dimensional space. But when you add 4-dimensional space, all of this comes back and it expands. It expands pretty quickly. 5-dimensional space gets even more tricky. And just as a reminder, that's how that worked. Okay, so with that in mind, we are going to, now that we understand that this actually does make sense, that means the left-hand side is a 1 form, right? Because as I said, the Hodge dual of the electromagnetic 2 form is another 2 form. The exterior derivative of a 2 form is a 3 form. And in 4-dimensional space, the Hodge dual of a 3 form is a 1 form, and J is a 1 form. So this is a 1 form, and this is a 1 form. All right, so now we have to calculate these things piece by piece and see what we get. And it's not going to be too difficult. It's all familiar, right? The Hodge dual of the electromagnetic 2 form is the Hodge dual of E wedge dx0 plus B, which is the Hodge dual of E wedge dx0 plus the Hodge dual of B, because the Hodge dual does distribute over vector addition. When I say vector addition now, I'm talking about the vector addition in the space of two forms, the vector space of two forms. So we now can blow this up, right? E wedge dx0 is E1 D1 E1 dx1 wedge dx0 plus E2 dx2 wedge dx0 plus E3 dx3 dx0. And we're now looking for the Hodge dual of that. And then I substitute in our form of B right here, and we're looking for the Hodge dual of that. So now we take the Hodge dual of dx1 dx0, and we get dx2 dx3. The Hodge dual of dx2 dx0 is dx3 dx1, and the Hodge dual of dx3 dx0 is dx1 dx2. And we use just the basic rules for calculating Hodge duals that I think I might have put. Yeah, I've rewritten them here, right? So dx2 dx0, you see 2, 0. It's going to be something with dx3 and dx1. I chose this order, 3 and 1, and the sign gets pulled out from the sign of 2, 0, 3, 1, which that is a sign of -1. But you pick up this epsilon of 0, which is the sign of dx0, of dx0 with itself, which is -1 in the case of the Lorentzian metric. So now these epsilon pieces actually start giving us a sign, right? Gives us a sign of -1. In other words, we're looking for the sign of dx0 wedge dx0. That's what we're calling, not wedge, inner product. And that's what we're calling, that's equal to -1. And that's what we're calling epsilon of 0, right? So this epsilon of 0 term right here actually gives us this -1, which counters that. So we have the Hodge dual of dx2 wedge dx0 is dx3 dx1. And this dx0 shows up for all of these Hodge duals of two-form basis vectors that include the time one form. But these Hodge duals do not. The Hodge duals of the purely spatial parts, because of the sequence we happen to choose. Now, this sign could have come up with a -1 had we chose, say, dx3 dx0 instead of dx0 dx3. This sign would have come up with a -1. But these epsilons would just give us positive ones. Likewise, over here, one of the epsilons always gives us a positive 1. Okay, but understanding that, and at this point, you should be familiar with how to do these Hodge duals. We've done it several times. So where did I go? So the Hodge dual of F is given by this expression, which is another two-form, right? But notice now that E is attached to purely spatial parts, and B is now attached to purely time parts, right? Which is interesting. So this is the dual of the electromagnetic two-form. If we were to put this in a matrix form, you remember the electromagnetic for tensor, when you write it in matrix form, the electric fields, when you put it in matrix form, right, the electric fields are on the edges and the magnetic field is in the middle where everything's diagonal, right? But the dual version, it swaps, right? The magnetic fields are on the edges because they are now the time component, and the electric fields are in the middle. So, and that's reflected here, right? Now you have the electric fields are associated with purely spatial components. Okay, and then the exterior derivative of the Hodge dual of the electromagnetic field tensor. That's a little bit more of a hassle to calculate, but we've done it several times, and we're expecting a 3 form, which is exactly what we get. And we get all these partial derivatives in there, right? And you can definitely see that now we're going to assemble these partial derivatives, and something like Maxwell's equations better show up. So you can work it out yourself. I'll leave it up here in case you want to see how I did it. This is the exterior derivative of the Hodge dual of the, this is the exterior derivative of the Hodge dual of the electromagnetic field two form. So we can kind of look in advance and say, okay, we know that we're looking for, we're trying to solve, what are we trying to solve? We're trying to solve, not solve, but we're seeking this differential equation here. So we're expecting, derivatives of the electromagnetic field with respect to time, and we're expecting cross products of B, so we should see differences in components of B, and we should see sums of some components of E, and then somehow we should see J0s and J1s in there. Well, we shouldn't see those in this part because we're only calculating the left-hand side, right? The left-hand side. So here's clearly time derivatives of the electric field right here, right? We see time derivatives of E. And we see some space. We see 3 space derivatives of E, and they look right. 1, 2, and 3. That looks like a divergence. And clearly here we see derivatives of B, and we know that we can subtract by once with like for example B partial 2 B2 3. I would expect that to, that's 201 201. Where's the other one that is 201? Right here, right? And partial 1 B3 1, right? So these two are going to subtract once we realize we want to turn this into 0, 1, 2. So that's 1 flip and then 2 flips. So that'll be the positive term. And this will be 0, 1, 2. And then this will be the negative term with 1 single flip. So it'll be this one minus this one, I guess. And, well, let's see. I think... Oh, no. What I did first is... There are going to be differences of these, but we're not done yet. We still have to take the Hodge dual of it. I forgot that. So we take the Hodge dual of these, because I kind of feel like the minus sign was in the wrong direction between these two. It should have been this one first minus this one. That's my intuition. But we still have to take the Hodge dual. So now you take the Hodge dual of this. So we're looking at the Hodge dual of these 3 forms. And I wrote those down here. Right, the Hodge dual of each of these 3 forms that are relevant. And again, it's the same rule, 0, 1, 2, 3. So we're looking for the sign of 0, 1, 2, 3. And then this epsilon of 0, epsilon of 1 of epsilon of 2. And the epsilon of 0 will give us a negative 1. So that's why we have minus dx1. And it turns out that they all give us a minus sign except for 0, 1, 3, which gives us a positive sign. And so when we do that Hodge dual calculation, we end up with these. It looks a little shorter because now all these 3 forms have become 1 forms, because the Hodge dual of a 3 form in 4-dimensional space is a 1 form. And now we can just kind of look at it straight up. I think I've organized this correctly. This material here is clearly the opposite of the time derivative of E, right? That's what this is. We just pull the partial 0 out, and we're left with minus partial derivative of E1 dx1, E2 dx2, E3 dx3, which is exactly what this is, where E is a 1 form now, a 1 form. And then this one is the divergence of E, the opposite of the divergence of E, partial 1 E1, partial 2 E2, partial 3 E3, but it's got a dx0 out there, so there's this dx0 hanging out. This is a number, remember, this is a real number, and this makes it a 1 form, but it's a 1 form entirely attached to dx0. And that's important. That's important. So this piece here becomes minus the classic vector derivative, minus the classical divergence of the vector field E with dx0. Now remember, there's no... So that association is very easy. And then the last one here, if you look at this, this is the Hodge dual of the exterior derivative of the Hodge dual of B. That's what this is, this last part. And so we can write down this final version, that the Hodge dual, because all this stuff is added together to give us what is it? I guess I should write that down. Hold on. Right, the Hodge dual of the exterior derivative of the Hodge dual of the electromagnetic field equals this expression here, the Hodge dual of the exterior derivative of the Hodge dual of the magnetic field minus the time derivative of the electric field one form, right? That's this, minus basically the gradient of E dx0. And we're going to say that that equals J. Well, J is minus rho dx0 plus the regular 3 current, J. Actually, that's not good because this is in vector form and we really want it to be just the one form of J. So we just want this J to be J1 dx1 plus J2 dx2 plus J3 dx3. It's supposed to be the spatial part of this, the spatial part of the J1 form. So it's just these pieces. So well, actually, it's best to look at it right here. The dx0 part is minus rho, and then the J part is right here. And that's what's on the right-hand side here. So now, when you look at this, this guy here and this here, these are purely spatial, right? This is the time derivative E, but E is totally a spatial one form, dx, E dx1, E dx, E2 dx2, E3 dx3. And this is also purely spatial, right? We can just look at it. You can see all of these covector parts are spatial covectors. So this is purely spatial. This is a number and dx0, so this is purely time. So you compare to the right-hand side, and this is purely time, and this is purely space. So we conclude that this part here must equal this part here, and this part here must equal this part here for this expression to equal J, where J is the full two form that we described right here, right? So in order for this to be true, these pieces, this part would have to equal this part, and this part would have to equal this part. Well, this part here, though, is just an expression of Maxwell's equation, the first of these Maxwell's equations, right? That's as simple as that. So we know Maxwell's equations are true, so we know that this coefficient and that coefficient equal, and so we get that condition. And this represents the curl of a magnetic field, and this is the time derivative of E, and it equals J. Well, that's exactly this expression here. So we know that's true for Maxwell's equation. So we know this part does equal this part, and therefore we know that this is true, and therefore we know that the way we modeled the electromagnetic field tensor and the construction of this exterior algebra actually takes those two Maxwell's equations and burns them into a single one. Phew, okay, so now we have demonstrated that these two Maxwell's equations can ultimately be expressed by the Hodge dual. I like to fill in these stars. The Hodge dual of the exterior derivative of the Hodge dual of the electromagnetic field two form equals the electromagnetic field, the current, the four form current. So now we have, and so that, and then the other one was dF equals 0. So these two very simple expressions give us the same information that's in Maxwell's equations, but look kind of how tidy this is, right? This is very, very, very tidy. And this tidiness is what should impress you, because it means that modeling the electromagnetic field as a two-form the way we have is somehow profound, because by doing that modeling, we get much simpler expressions for the underlying physics. And so interpreting this F is actually worth our time to see what is it that it's trying to tell us about the electromagnetic field? First of all, I think it is telling us that we live in a four-dimensional world, right? Because when you add that fourth dimension, things tighten up very, very much. And for physics, this is a really beautiful thing. For engineering, though, you're kind of just going to do what we've always done. I don't think there's any advantage for engineers to immediately jump into this necessarily. I'm going to check on that. I'm going to find some engineering problems that do, in fact, start from this posture. I feel like even if they did start from this posture, they would actually start from the three-dimensional version of this, right? You can do this in 3 dimensions as well, and these equations become a bit messier, right? You end up having to insert time derivatives by hand, where the 3 space derivatives are all taken care of in the vector formalism. But the point of this lesson is to show that we can get these 4 equations down to 2. But you'll remember we've already gotten them down to 2. We did it several lessons ago, where we got them down to these 2 potential equations for the scalar potential and the vector potential. Now notice these equations are, relatively messy, right? You still have time. You have your space blended up in here, by the way. So you see time and space are definitely the actors here, but they're not merged into a single a singular formalism. They're still separated, right? And because of that separation, you have to kind of work a lot harder with special derivatives of things and rules and everything like that. But here's this is obviously in different units, right? This is in units where C is not equal to 1, and right, the other material we did just a moment ago, these units were different. But you still see the charge densities here, the current is here, and now it's all the vector form. But still using the vector form, we got Maxwell's equations jammed down into 2 things. So our final question that I'm wrestling with, playing with, and I just don't think I'm going to be able to resist the temptation, is to ask the question: is there a formalism that can take these 2 guys, these nice 2 guys here, and squeeze it down into a single equation, a single expression? Is that possible, right? And my understanding is that it is, but now I'm going into a field that I have yet to fully familiarize myself with, a field called geometric algebra. And it is very interesting, and I think I am going to not be able to resist the shiny object of going and studying geometric algebra. And it'll be more of an adventure where we learn it together because, well, I know quite a bit about it already, but not enough to, in order to get to the level of teaching it, it will be a bit of an adventure. I'm not sure if I should continue it on as a tangent in the QED prerequisites, because it's definitely not a QED prerequisite. Even this is not a QED prerequisite, right? We did the QED prerequisites earlier. This is all a shiny object tangent. But to go into here is really shiny object territory. And, I know myself well enough to know that I'm not going to be able to resist. So, sooner rather than later, we'll probably begin a sequence in geometric algebra and hopefully finish it. Okay, so there we have it. This is how differential forms are applied to the theory of electromagnetism. And I'll see you next time.